Assalamualaikum warahmatullahi wabarakatuh. Welcome back to our lectures of hydraulics. Right now we already in the fifth week. Okay, so today's lecture we will still talk about the flow kinematics in the open channel, part two, because last week we also talk about the flow kinematics in the open channel. Okay, so last week we talk about the flow kinematics in the open channel. We talk about the velocity, the discharge. Okay, how to calculate the discharge with general equations, and also other uh, kinematics parameters, okay, in the flow. Okay, so today we will still talk about the velocity, the discharge, but in this lecture we will talk more specific how to calculate the velocity and also the discharge with the consideration of the roughness factor. Okay, so in this lecture we will consider, or uh, we will we will consider the roughness factor that impact the velocity and also impact the discharge. We will talk more specific about that in this lecture, because maybe if you still remember our last lectures last week, when we talk about the velocity, we remember that the velocity in the open channels is not always the same in the cross sections. Okay, so there is the velocity distributions happening in the cross sections of the channel, because uh, there is a influence. Okay, there is an influence from the bottom of the channels and also from the wall of the channels. Okay, so we know that uh, the uh, the close the flow to uh, the bottom or the wall of the channel, the less the velocity. Okay, so because there is uh, the influence from the bottom and also from the wall. Okay, maybe because there is a roughness in the bottom and the wall, so it impact the velocity eh, that flowing uh, near or close to the bottom and the wall of the channel. Okay, so but last week we we talk about the discharge, and we calculate the discharge using just this using these general equations, right? Q is equal to A times V. Okay, this is the general equation of the discharge. And today lectures we will more specific talk about the roughness, okay, that impact the velocity. Okay, so we will consider, or we will input the roughness parameter into the calculation to get the velocity, and then from that velocity we can calculate the discharge. Okay, so that's what we will talk in these lectures today. Okay, so if we talk about the roughness or the friction factor. Maybe some of you remember about the Darcy waste bay, okay, from when we learn about pipe. Okay, we know that there is a head loss or energy loss because of the frictions from the pipe, uh, and we can calculate from the equation of Darcy waste bay. Okay, and if you remember the equation of head loss because of the frictions is, or HF is equal to the friction factor times the length of the pipe times the velocity square over 2 g times d, the diameter of the pipe. Okay. um, and if we talk about the open channel flow, okay, the open channels, we do not using diameter parameter. Okay, we use what we call as hydraulic radius, or R. Okay, so R is uh, the 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 area of the wet surface over P, the perimeter. Okay, so if you remember, hydraulic radius is, if you want to calculate the hydraulic radius, we are we need the wet surface, okay, from the cross sections of the open channel over uh, the perimeter of the wet uh, the perimeter of the wet of the open channel. Okay, uh, for example, if the channels is rectangular and this is uh, the water is until this, the surface of the water is here, and this is the bed of the channels. uh, this so the wet parameter, the wet area A is this, yes. Okay, the area of the wet surface in the cross sections of the open channel. Okay, and the perimeter, which is also only the wet area, is from this height. So this height, uh, some this height, some this height. Okay, uh, if the channels until this height, we only measure the wet area. Okay, so the perimeter, we calculate the perimeter only with the wet area. Okay, we do not include this height that not that not have a wet. uh, okay, so we just calculate until the surface of the water. Okay, that's the perimeter. So if this is B and this is Y, so A is B times Y, and P is B plus 2Y. Okay, okay, so this is the hydraulic radius. We do not use diameter for the open channel, we use a hydraulic radius. And if we look for the connections between the hydraulic radius in and also the diameter, we know that a pipe is circle shape. So uh, if we uh, if we use the circle shape, okay, so this is the area, which is if the circle, so the area is uh, 1 over 4 times uh, P times D square, right? Okay, and so we can write it in here. And the perimeter of the pipe or the circle shape is P times D. P times D, okay? So we will end up get R is equal to D over 4, okay? D over 4 here, okay? And also we know that the slope of the channel is equal to the head loss because of the roughness of because of the frictions over length. So if we uh, write the equations and then we substitute the diameter into the uh, R, so R is equal to D over 4, so D is equal to 4 times R, right? So we will get this, and the length will eliminate because SO is equal to HF over L, so L over L, okay? Okay, so we will get these equations for the slope of the channel, and from that we will get the uh, the frictions number for open channels is here, okay? So we can write in these equations. So this is just the white pictures, yeah. This is the big pictures to explain to us what really impact, what parameter that really impact the frictions factor that we will talk in these lectures, okay? There is a gravity, and also the hydraulic radius, and the slope of the channels, and also the velocity. So this parameter will impact the friction factor. Also, if I say what impact the velocity, uh, uh, if we consider um, uh, friction factor, and also the open channels characteristics, yeah, we know from this slide, from these big pictures, that what the parameter that impact the velocity is the hydraulic radius, okay? So this is uh, the open channel open channels um, characteristics, okay? And also the slope of the channels, and the gravity, and also the friction factor, okay? So that's why we will, in this lecture, we will consider the friction factor in into the velocity calculations, okay? Okay, in this lecture we will talk much about the roughness or the friction factor from many equations, okay? But that equations is generally from the assumptions of the flow is the uh, uniform, okay? So a uniform flow mostly assume in this roughness factor that we will talk about in this lecture. So we need to more specific to understand the content of the uniform flow. Okay, that many equations use uh, when they create when use and use these assumptions when they create the roughness equations. Okay, or the velocity equation that consider the roughness factor. Okay, so in this schematic in the right side, okay, this one, yeah, okay, this one, um this is we have a flow in the open channels. This is the bed, okay, and this is the surface of the water, okay, and the open channels have a particular slope, yeah, with this angle theta, yeah, theta angle. So this the channel have a certain slope with the theta symbol. Okay, so I want to introduce this imaginary line, okay, or boundary line that this is one system of the water, okay, with this imaginary boundary line. So this water have a particular length, okay, L. Okay, so this is the imaginary boundary line that we will focus on this water with this particular length L, and this is and this water have a wake. Okay, so have a wake which because of the gravitational uh, force, yeah, which is equal to the wake of the water in here. And also this water also flowing with a certain velocity. Okay, because of this water is flowing, um, there is a shear force occur in the bed or in the bottom of the channel and also in the wall of the channel. Okay, so there is a shear shear stress or shear force, okay, tau, that that happening in this particular water. Okay, that that giving a shear force into this into these directions. Okay, okay, so first of all, when we look at the gravitational force, yeah, gravity force, what what happening in gravity force is in this water is actually equal to the wake of the water. Okay, so the gravity force that occur in this water is equal to the wake of the water. Okay, so we know that wake, yeah, w, this w symbol for wake is equal to mass times gravity. Okay, And we also remember that mass is equal to density times volume. Okay, because maybe some of you remember the density is equal to mass over volume. So mass is equal to density times volume. Okay, so if we write the weight with the density, we can write as density times volume times gravity. Okay, so and then this weight also uh, act as a gravity force in this case. Okay, so if we look in here, okay, gravity force, which is equal to weight. Okay, uh, we know that weight is rho times g times v. Okay, from here, rho times g times volume. So this is rho, this is g, and A times L is the volume. Because uh, if I make this schematic three-dimensional, okay, for example, okay, I hope okay, okay, if I make it three-dimensional, so there is a water that flowing here in certain length. Okay, so this area, this uh, this surface, this cross-sectional area of the wet surface is A. Okay, this is also A. Okay, and this length is L. Okay, so if I want to calculate the volume, so the volume is A times L, right? Because if I assume this is a because of the boundary, because the imaginary boundary line of this particular water, we can assume this is the shape of this water systems is rectangular. Okay, so if I want to calculate the volume, I calculate the cross-sectional area, okay, times the L. Okay. From the front side, yeah, this is A, this is area, okay, and okay, and this is L, the length is L. So if I want to calculate the volume, simply I calculate A times L, right? So A times L here is equal to volume, okay, of this particular water. And uh, we times sin theta, because the wake, which is the direction, down direction, because the channel is not flat. Okay, there is a slope here, there is a slope here, this is not flat, so we must calculate the sin theta. We must include the sin theta into the calculations. So times sin theta, because uh, the the bed of the channel, the bottom of the channel is not flat. This there is a slope here. There is a some angle slope that made the bed have a certain slope. Okay, so we need to include the sine theta into the calculations. Okay, so this is the gravity force that happening in this water systems. Okay, and then there is also the tow, right here, the shear force that happening because of the bottom of the channel and also the wall. There is a the frictions. Okay, there is a frictions uh, that make the shear force happening in the water. Okay, so the shear force is tau times p. Yeah, uh, p is what's uh, tekanan ya, pressure. Okay, and also the length. Okay, so this is the pressure, the shear force that happening. And in the uniform flow, we talk about uniform flow here. In the uniform flow, there is a balance between the gravity force and also and the shear force. So uh, when the shear force and the gravity force is balanced, uh, that will create the uniform flow. Okay, so the shear force is equal to gravity force. This is the uniform flow. Okay, and uh, if we look in the open channel that have a very small slope angle, yeah, theta, we can assume that sin theta here is equal to the slope of the channel, which is SO. Okay, because uh, we we neglect the sin or the tan because the theta is uh, really small, uh, almost flat. Yeah, so we can say it equal to the slope of the channel itself. Okay, so if we sin theta, we use SO to in the sin theta, we ended up have these equations. Okay, rho g a time sin theta over p. We eliminate the L because the L is will uh, L over L, yeah, so we eliminate L, so we will get these equations. Okay, and we remember that A over P A over P is equal to hydraulic radius, which is R. So we can write in this form, yeah, rho G times R times SO. Okay. Okay. So this is why we talk about this, because this is the philosophy of the roughness or the frictions that we will talk in this in the another slide. Yeah, that what really what parameter that really impact the shear force because of the frictions or because of the roughness is uh, hydraulic radius, the slope, the density, and also the gravity. Okay. Okay, now we will the first equations that uh, consider the roughness into the calculations of the velocity is what we call as Chasey equations. Okay, so this Chasey equations is uh, very famous. Yeah, we we still using the Chasey equations until this time. Okay, when we calculate the velocity, or well, when we calculate the discharge in the open channels. Okay, so Chasey assume, yeah, uh, Chasey assume, yeah. So Chasey, someone from uh, okay, so Chasey is a researcher, okay, from many times ago. Okay, so Chasey assumed that in the turbulent flow, the frictions factor or the frictions. Um, I'm sorry, I need to answer my phone. I will pause. Okay, we continue our lectures. So, Chessie assumed that in turbulent flow, the friction's force is almost equal to the um, I'm sorry, another phone. Okay, I'm sorry. Let's continue. Chessie assumed that in turbulent flow, the friction's force is almost equal to the uh, velocity square. Yeah, or if we so the shear force, okay, is almost equal to the uh, velocity square. Okay, this almost equal thing is what we call there is something here. Okay, there is something here that make it almost equal. Okay, that something is some coefficients. Okay, so the shear force is equal to some coefficient times velocity square. Okay, so this some equations this some coefficients that Chessie uh, assume that what we will what we will learn here. Okay, so this is from last slide. Okay, so from that we can uh, we can uh, if we use this, yeah, into this. Okay, and phi square. Okay, so phi is equal to, so the square is become the roots. Okay, and rho g something uh some coefficients times r time times r, so rho g times r times so. Okay, so rho g times r times so. Okay, okay, rho g r so is equal to some coefficient times v square. Okay, so we when we will when we calculate the V is equal to root of the rho G R S O over K. Okay, this K later we know as the Chesky coefficients. Okay, in the Chesky equations, and Chesky use a C symbol to write or to write the Chesky coefficients. Okay, so so Chesky use C. Okay, so phi. Okay, so the rho G over K. Okay, become the coefficients of Chesky. Okay, so Chesky coefficients already consider the density, the gravity, and some coefficients for the Chesky coefficient, which is the roughness factor of Chesky. Okay, so when we calculate the velocity and we consider using the roughness or the coefficients of the chassis, we use these equations. So phi is equal to C, which is chassis coefficients of the roughness times the root of R times SO. Okay, so velocity is equal to chassis coefficients times roots of the hydraulic radius times the slope of the channels. Okay, okay, so we already understand how chassis assume how the philosophy of these chassis equations, and we already know how to calculate the velocity of the flow in the open channel if we using chassis equations. Yeah, I state chassis equations because in next slide we will talk another coefficients, yeah, another roughness or another friction factor, uh, or another roughness coefficients that introduced by another persons, yeah, commenting, yeah, not chassis. So C is for chassis, and we will learn another one in the next slide. Okay, if we want to know how the connections between the C chassis and the F of the Darcy-Weisbach, so C is the friction factor of the chassis, or we can also say it as a roughness, yeah, roughness coefficients of chassis, yeah, and F is the friction factor of the Darcy-Weisbach in the pipe, yeah. um, we will get the connections that C chassis is equal to root of 8 times G over F. Okay, so this is the connections between the roughness factor of the roughness coefficients, or we also can say the frictions factor of chassis and the friction factors of Darcy-Weisbach. Okay, okay, let's look for example. So we have an example here. There is a rectangular shape of the open channel. This is the rectangular shape. Uh, uh, the open channel. This channel have a 5 meters long of the bed of the channels or the bottom, we can use the symbol B for the bottom or bed. B is equal to 5 meters. And the hydraulic, not the hydraulic, the flow depth, yeah, the flow depth in this channel is Y, which is 1.5 meters. Okay, so we know B is equal to 5 meters from this example, and Y is equal to 1.5 meters. And also from this example, from this task, there is also another information, which is the slope of the channels. Okay, so the SO is 0.0005. Okay, and also the information from this task, there is a Chesy coefficient C is equal to 40. What they want us to find is the discharge Q, how much discharge that flow in this uh, open channels in this problem. Okay, in this example. So first of all, we remember the Q equations is A times V. Okay, so A is the cross-sectional area, this one, the wet area, the area of wet, the cross-sectional area. Okay, and V is the velocity. Okay, so we will calculate the velocity using that include or that consider the Chesy coefficients into the calculations, which is C times root R times SO. Okay, from last slide. Yeah, this is C of the Chesy. R is hydraulic radius, and SO is the slope of the channels. Okay, so C, we already have the data here, 40, and SO also we already have 0.0005. So we need to find the hydraulic radius R, which is A over P. Yeah, uh, so uh, if we want to find R, we need to find A. Yeah, so A, the cross-sectional area, is simple, B times Y. Okay, this is B, this is Y. Yeah, so B is 5 meters times 1.5 meters, so it is 7.5 meters. Okay, so we get A 7.5 over P. Yeah, P, we remember P is perimeter, which is if the shape is rectangular, we simply calculate P by B plus 2 times Y. Okay, B is 5, 2 times 1.5. Yeah, so this is equal to 8 meters. So this is 8 meters. Okay, so this is and we ended up find R. Yeah, we find R, we already know the SO, we already know the C 40. We can calculate the fee. When we already calculate the fee, we have the number here, and also we already have A. We can calculate the Q, the discharge. Okay, so let's moving on. So this is the answers of the problem. So B is 5.0 meters, and flow depth 1.5 meters. The slope of the channels, this is the cross-sectional area, B times Y, which is okay. Sorry, I forget this meter square. Okay, sorry. And this perimeter is b plus 2y. We get 8 meters, and then hydraulic radius a over p, which is 0.9375 meters. And then the velocity, we already know the chassis coefficients. We input the r here and then the so, and then we get the velocity 0.866 meter over second. Okay, and then discharge a times v, a from here times v, and we ended up we get 6 times 4 9 5 meter cubic over second. Okay, okay, so this one is a very easy problem. We skip this. We already talked about this in this in the week 2 or 3. Okay, now we know in this slide, as I mentioned earlier, that there not only chassis, okay, not only chassis equations that introduce the roughness factor that we can consider into the calculation of the velocity if we want to know the velocity of the open channel flow. But there is also another person called Manning, or Robert Manning, from this time, yeah. So Robert Manning also introduced the roughness factor or roughness coefficient, which we call as Manning coefficients. Okay, so chassis is chassis coefficients, Manning is Manning coefficients, right? That uh, which is considered the roughness or the frictions factor of the open channel. So this Manning equation also very popular. We also use these Manning equations uh, until today. Okay, we want to calculate some flow parameters in the open channels, and Manning also assume, yeah, uh, the flow is a uniform flow, yeah, uniform steady state flow, yeah. So when Manning built this equation, he assumed the flow is in the uniform steady state flow conditions, okay, with with free surface, okay. Okay, so if we want to calculate the velocity using Robert Manning, using Manning equations, sorry, using Manning coefficients, we use these equations, yeah. So times SO times R, okay, because A over P is R, okay. So this N is Manning equation, okay. Manning, sorry, this A is Manning coefficients, okay. So V is equal to 1 over N times SO, and yeah, this is the equations. So I already mentioned that Manning use uniform steady state flow assumptions when he create these equations. And if we talk about the uniform steady state flow, we know that the slope of energy is equal to the head loss over L. Yeah. So it's almost similar with what we already talked about in the first slide. Yeah, so the slope of energy in the uniform steady state flow, we know that the slope of energy is equal to the slope of the water surface, and also equal to the slope of the bed of the channel. Okay, and R is the hydraulic radius, right, which is A over P. Yeah, this is R, so I write in this equation as R. So how the connections between the N Manning, yeah, and the C Chasey, both use introduce some roughness coefficients. Manning introduced N as a roughness coefficient. Chasey introduced C as roughness coefficients that will impact the velocity. Okay. So how the connections, how these two um, equations, so C is equal to R uh, over N. Yeah, so this is Chessie, okay, is equal uh, with this. So this is N Manning, this is Chessie. Okay, okay, so this is the Manning. Yeah, we as we can see, Manning also, when we calculate velocity with consider Manning coefficients, and we can see that in this velocity, we also consider R, SO, yeah, R hydraulic radius of the open channels, SO the slope of the open channels, and also the roughness coefficient from Manning. So it's almost similar with the chassis, right? Chassis also. If we want to calculate velocity with chassis, we also consider R hydraulic radius. We also consider the slope of the channels, yeah, and also the roughness coefficient from chassis. Yeah, there is R, there is SO, similar here. There is R, there is SO to find the velocity. What different is when we use Manning, we use these conditions. Yeah, when we use chassis, we use this. Okay, so if we want to calculate the velocity using Manning equation, we use these equations. It's similar what I am right here. R 2 over 3, SO 1 over 2, right? R 2 over 3, so over N. And if we want to calculate the discharge, we know Q is equal to I over I times V. Yeah, so this is, sorry, so this A over P, which is R, right, from here, but it becomes, because we calculate also with A to calculate the Q, right? So this is how to calculate the discharge with consider Manning equations. So this is equal to K A times V. Yeah, so V from this times A. So we ended up with these equations Q. Okay, so maybe some of you want to know how the number of the n Manning. Yeah, so it depends on the channel type. Yeah, if it's river with the earth and the foam is strike, the Manning number or n number in the range of this number, right? If it's a line canal, yeah, with concrete, we can use this n Manning number. uh, if rock, uh, form strike, we can use this. Okay, so it depends on the channel type, and also depends on the surface materials and the form of the open channels. And I can also tell you that chassis, if we talk about chassis, there is also this kind of chassis uh, number, yeah, that also depends with the channel type. Yeah, in the sum of the problem here, uh, we just have one example of chassis number, which is 40. But maybe if you looking at another book or another reference, you can searching for chassis coefficients. Yeah, maybe you will get uh, 20 and 30, yeah, for particular channel type, or for particular surface materials. Yeah, maybe 30, yeah, for the number of chassis coefficients for particular uh, uh, channel type or surface materials. Okay, and this is Manning. Yeah, um, if it's gravelly, for example, yeah, uh, this excavated earth channels, we can use Manning number. Yeah, is this right? Use natural streams and uh, clean and strike, we can use this Manning number. Okay, if it's asphalt, we can use this, or if wood, yeah, we can use this. So there is many book or that will uh, give us the number of the Manning coefficients, and also the Chessie coefficients. So another example problem. So there is a open channel with rectangular shape. Uh, the B here, yeah, the bottom or the bed is 6 feet, and the Y is 3 feet. Yeah, Y or flow depth. Okay, and the slope, yeah, the theta is 2 derajat. Yeah, and the friction factor is 0.022. Yeah, we use friction factor here. Yeah, and they want us to calculate the discharge. We also get the G here. Okay, so because this F is appear in this task, I assume that we will answer this problem with Chessie equations, with sorry with Chessie coefficients, to calculate the phi, and then to calculate the discharge. Okay, let's see the answers. Okay, so as you remember, Chessie, yeah, and friction factor, the connections, as we talk um, in the first slide. Okay, here, here we use this to answer the problem. Okay, so we already know the G from the text, and we know the F from the task, and we can calculate the C. Okay, and then of course we need to calculate the A, which is B times Y. Okay, and then next we calculate the hydraulic radius R, which is A over P, right? This is equal, this is Y plus B plus Y, right? This P, right? And then we get this number, and then we know that SO is equal to tan theta, which is, we know from the text, the theta is 2, right? 2 2 derajat ya. So tan 2, and then we calculate the Q. Yeah, we know Q is equal to A times V. Yeah, the phi we use here is the phi that considers C, chassis, times roots of R times SO, right? Or we can write in another form, C times R over 12 times SO, like this. Yeah, okay, R, SO, and C. Yeah, this is velocity, and if we want to calculate the discharge, we must calculate it with A, right? So that's why there is A appear here, because we calculate the discharge. Okay, so this is a V, volume, sorry, velocity, and this is A, right? So Q is A times V. So we input the number, and then we get this 40 and 50, yeah, feet cubic over second, yeah, for discharge. Okay, so that's how we answer this example problem using what we already learned in these lectures. Okay, so that is the end of our lectures today. I hope um, everybody can understand. I'm sorry if many of you maybe cannot really understand my English, because I still learn to uh, speak English properly. I'm sorry, but I really hope you can try to learn not only from these lectures, but also from the book, from another lectures in the YouTube, or another uh, to learn. Yeah. Okay. I I say thank you very much from your attentions. If there is a questions, you can uh, send to me your questions. Okay. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh.